All right, so we're going to start with page 256, 2D. Okay, so make sure you let me know if you need me to stop or if you have any questions. All right, 256. All right, so here they want us to find the derivative, and it looks like we've got y equals sine x over 1 plus cos x. Okay, so let's take a look at this here. So here, clearly, we're going to have to use the quotient rule. Okay, so derivative of the numerator, cos x, times the denominator function, 1 plus cos x. Okay, and then minus the numerator function sine x times the derivative of the denominator function. Derivative of 1 is 0. And so derivative of cos x is negative sine x. And of course, all of that over 1 plus cos x squared. Okay, and if I'm asking you to just take the derivative, not simplify, you can leave it as is. But here, kind of looks like we might have some nice simplifying, because right away I see a cos squared, and then that's going to give me a plus sine squared. So it looks as though this might have a chance of course, that's a derivative. So let's just distribute this out. So we got cos x plus cos squared x there, and then here plus sine squared x, and then of course we know that's equal to 1. And so when I simplify that, in fact, I'll write the 1 in front, because now it looks as though I got something really nice that happens in the numerator and the denominator. And all of a sudden, this factor of 1 plus cos x in the numerator cancels out with one of the 1 plus cos x's in the denominator. So it looks like we're left with 1 over 1 plus cos x. Okay. So in the end, we're seeing how we can use our trig identities to simplify these as needed. So again, it's very possible that I might ask you to just find this derivative without simplifying. You can stop here, but you can see that you can move on and get to a derivative that's much, much simpler to work with if you need to. Okay, any questions on that there, especially from the person who asked? No? Okay. So let's move on. So next I had 14. So what's going on in 14? Okay, yeah, 14 is actually a very interesting problem, because it's an example of what we call a differential equation, meaning an equation that involves derivatives. Okay, and while we're certainly used to equations that involve functions, so especially if you're trying to find the x-intercept, you're just setting the y equal to 0. Sometimes you might have equations that involve derivatives. So here they give us this function, okay, which is made up of a cosine function and a sine function. So it's a cos kt plus b, assuming sine kt. Okay, and they tell us that a, b, and k are constants. So that's going to be important, especially since I see we're going to have to take some derivatives. And then they want us to show that this equation, or this expression on the left, that the second derivative of y plus k squared times the function itself is equal to 0. Okay. So here's our function. This is what we're trying to show is true. So clearly, the first thing we're going to do is find the second derivative of this function. All right. Of course, to find the second derivative, we need to find the first derivative first. Okay. So this is where I'm just going to be very careful. So so here I've got the sum of two functions. So I'm going to treat them individually. First to take the derivative of that, then take the derivative of that, and the sum of those two derivatives. So here, if I'm just looking at this first function, a is just a constant. I don't need to worry about that. And here, I know how to find the derivative of, in this case here, I'm not going to be talking about the variable x, but the variable t. I know how to take the derivative of cos t, but I don't have cos t. I have cos of a constant times t. So I need to use the chain rule. Okay, so anytime the input is anything more complex than just the variable itself, I'm going to need to use the chain rule. So I'm not going to write it all out. I'm going to do it in my head. So I'm going to let this kt be equal to my u. So the derivative of cos u is just negative sine of u. And then I have to take the derivative of u with respect to t. So k is just a constant times the derivative of t with respect to t is just 1. So I'm just left with an extra constant t. Sorry, of k. Any questions on how I took this derivative? Okay, because I'm essentially going to be following the exact same maneuver with all the other derivatives I have to take, because here b is just a constant. The derivative of sine u is just cos u. And then the derivative of u with respect to t is just the constant k, because the derivative of t with respect to t is just equal to 1. Okay, so one thing I do want to mention is because they're using prime notation, okay, they didn't tell us what we're taking the derivative with respect to, but because the variable happens to be t, I'm taking the derivative with respect to t. If the variable was x, I'd be taking the derivative with respect to x. Okay. So now I'm going to clean this up before taking the second derivative. So this is when you need to work with a derivative. It is good to simplify it. So here I'm going to have a negative. I'm going to have my two constants, a, k, and then I'm going to be left with sine of kt. And then here, plus my two constants, bk, we usually write those first, and then times the function cos of kt. And now I'm going to do the exact same thing to find the second derivative. Here, negative ak is just a constant. So I can take that out of the derivative. And again, I'm going to have to use the chain rule. Okay, but since I've already taken the derivative sine kt, I can just copy it from what I have here. I know it's just going to be cos of kt times k. Okay, here bk is just a constant. I've already taken the derivative of cos kt. I might as well just copy it from what I had before. It's going to be negative sine kt times k. Okay, and now before I put it back into the equation, let's clean it up. I've got my negative a. I've got two factors of k, so k squared times cos kt. And then here, I've got a subtraction now. b times, again, two factors of k, so k squared times sine kt. And now that I have y double prime, and obviously I know what y is, I can stick it into my equation. So let's take the left-hand side, because I want to show that this is true. So I'm going to start with clearly the left-hand side has more opportunities for algebra. And I've got my second derivative, which is negative a k squared cos kt minus b k squared times sine kt. And here plus k squared times the function y, which is of course that thing up there, a cos kt plus b sine kt. And you're probably going to see what's going to happen here, because this a k squared cos t cancels out with this k squared times a cos kt. And then this negative bk squared sine kt is going to cancel out with this one here. And lo and behold, we're left with 0, which is the right-hand side. Okay. So here what we have is we've shown that this equation is indeed satisfied. That if I start with this function, which is a combination of these two trigonometric functions, that if I take the second derivative plus k squared times the function, that would be equal to 0, regardless of what the variables a and b, sorry, the constants a, b, k are. and for any values of t. Okay. Now, just to give you a heads up when you would see this type of equation, well, remember, cos and sine represent wave functions. And for those of you who've taken physics, you know that often we add wave functions together. Okay, so when you have two waves that interact, it's like adding those two functions together. Okay, and of course, how do we get different amplitudes and different periods for our waves? We get that by having vertical stretches and horizontal stretches. Okay, so for those of you especially doing physics or engineering eventually, you'll see these types of equations all the time. Okay, any questions on this here? So just to recap, the idea is to find the things inside the equation so you can plug them in. And of course, just as important is being exceptionally careful with all the arithmetic, because you can see any one sign error and this was not going to work out as needed. Okay, so if there's no questions, we'll move on to 260, number 4A. Okay, so let's take a look at this here. So 4A. So here again, we're finding the second derivative of this function here. So y equals sine x tan x, sine x tan x. And we want to find the second derivative. Okay. So let's start by finding the first derivative. So here this time, we're going to have to use the product rule. So derivative of the first function, cos x, times the second function, okay, plus the first function, times the derivative of the second function. So derivative of tan x is secant squared x, okay. And now I just need to take the second derivative. Now, one thing I would consider doing here is I look at tan x, and I know tan x is sine over cos, and I'm multiplying by this cos x. So I'm very tempted to, hey, do some simplifying. Here, I guess I could put this secant squared as 1 over cos squared. Nothing stops me from doing that, but I don't know that I'm going to gain much out of that. But here I definitely get to simplify my life. And even better, I see that there's a common factor now of sine x. And I'm just left with 1 plus secant squared x. Okay, so this just feels like a much easier expression or function to take the derivative of than the original one there. So if you had used this original one, perfectly fine, although you would have had to use the product rule twice, along with, we'll see here that we're going to need to use a chain rule, but sometimes doing a little bit of simplifying before I move on is helpful. So any questions on how I simplified this? No? Okay. So let's move on to the second derivative. So now I'm going to do the product rule again. So here, derivative of sine is just cos times 1 plus secant squared x. Okay, then plus the first function, sine x, times the derivative of 1 plus secant squared. So derivative of 1 is easy. It's just constant, so 0. Here, though, I'm going to have to use the chain rule. Okay, so my secant x becomes like my u. Okay, so the derivative of u squared is just 2u. So 2 times secant x. And then I have to multiply that by the derivative of u, so secant x, which is just secant x tan x. Okay, now remember what I said for the test. I don't expect you to know these derivatives, so you probably wouldn't have a question exactly like this, but you want to make sure that you are able to do it. Okay, so let's see if we can simplify this a little here. So we've got a cos x there. Now, I'm going to save myself a little bit of time, or try to, because here, when I do this multiplication, I know this is 1 over cos squared. So I've got a cos x in the numerator, cos squared in the denominator. I'm going to cancel out the cos x in the numerator, the cos x in the denominator. So I'm just going to be left with 1 over cos x, which is secant of x. Okay. Now, if you're having any question about this kind of product, you really should just write it out. Okay. I decided to do it in my head. Let me know if you want me to show on the side how I got that. Okay. So let's see if we can do anything here. So I don't know, this is not particularly nice, but maybe I will write it out. So that's a 2. These are all multiplications, so I can just change the order as I want. So I've got the sine x. I've got 2 secant x's, so 1 over cos x and squared, because I got 2 of them. And then I've got the tan x, which is sine x over cos x. So there's nothing really that cancels out, but I guess I can bring some stuff together here. It looks like I've got in the numerator, I've got a 2 sine squared. And then denominator, what do we have? Looks like we have cos cubed x. You could turn this, sine squared over cos squared is tan squared, and the leftover 1 over cos could be a secant. I guess essentially what we had here, which one is simpler is really more up to your feeling. So something like this, or even leaving it like this, just maybe putting the 2 in front. Either way, bringing the secant squareds together. It's not really that important how you write it out. Okay. But in the end, the important thing here is to realize that you needed the product rule. Okay. A little bit of simplifying made taking the second derivative much easier. And then from there, you just needed to use the product rule and the chain rule to do that. Okay, any questions on this one here? No? Okay, so the big takeaway from all these questions so far, especially the last 2, is really be careful on taking each individual derivative, okay, to avoid any little error that could turn it into a much more difficult question. Okay. So what do I have next? So next we had page 110, 28G. Okay, so that's actually on page 113. So that is page 113, 28G. And let's see what they're asking for. And they're asking us to determine the derivative here. Okay, so 28G, so we have g of x is equal to 2x plus 5 all over 6 minus x squared. And this is all to the exponent of 4. Okay. So in this question here, what I'm seeing is this function inside my bracket will just be my inside function. And so my outside function is just some variable to the 4. So I'm going to let this be my u. All right. So when I take the derivative, I'm taking first the derivative of the outside function. So the derivative of u to the 4 is 4u cubed. And now I'm going to multiply that by the derivative of that inside function. Of course, the derivative of that inside function is going to require the quotient rule. Okay, so let's try to carefully do that. So derivative of the numerator, it's just a linear function. So it's just 2 times the denominator function, 6 minus x squared, then minus the numerator function, 2x plus 5 times the derivative of the denominator function. Luckily, we got that 6, which is a constant, so derivative is 0. So it looks like we just have negative 2x. Okay, and all of that is 6 minus x squared, all squared. Okay. And again, if I was asking you to just find the derivative without simplifying, you would stop there. Okay, but let's see if we can simplify. Okay, so here, because I see that 6 minus x squared appearing in both of these denominators, I think what I'm going to do is distribute that exponent to both numerator and denominator. Since it's a division, I can do that so that I can bring together some terms. So here I've got 4 times 2x plus 5 all cubed, all over 6 minus x squared all cubed. Okay, of course, the exponent 3 doesn't apply to the 4. And so I'm going to bring those together at some point. But in the meantime, let me distribute my numerator. So what do we have? We have 12 minus 2x squared. Okay, and then here we've got negative 2x times 2x is 4x, negative 4x squared. But then there's a negative in front, so that's going to be plus 4x squared. And then here I've got negative 10x, but of course I've got this negative in front, so it's going to be plus 10x. Okay, and again, if you might be better to do that in 2 steps, but if you're comfortable doing that in 1 step, all the better. Okay, and now we can simplify. So we've got our 4 times 2x plus 5 all cubed. Here, let's see what we've got left in our bracket. So negative 2 plus 4, so we've got a 2x squared. Then here we've got a plus 10x, and then it looks like we've got a plus 12. Now I'm going to bring together these two denominators, 6 minus x squared all to the 5. Okay. And I notice that I can go a little further. I can factor out a 2 there. So if I factor out a 2, there's another factor of 2, so that's going to be 8 times 2x plus 5 cubed. Let's see what we have left here. We have x squared plus 5x plus 6. Okay, all over 6 minus x squared all to the 5th. Okay, and here, hey, look at that. We can go even further because, of course, 2 and 3 add up to 5 and multiply to 6. So this one, we can really go pretty far in terms of the simplification. Okay, x plus 2, x plus 3, all over 6 minus x squared, all to the 5. So unless I made some silly error there, it looks like this is as far as I can go. So you have to imagine that, say I wanted to determine when the derivative was equal to 0 or the derivative didn't exist, it would be very easy to tell because I have it all in factored form. Okay. So again, it's very likely that on this test here, I might ask you to just stop at that point in the process, but eventually say I needed to use this derivative to help me determine some characteristics of this function, which is something we're going to focus on in the next unit, then I would be very motivated to simplify as far as I can. Okay, any questions on this? Nope, okay. All right, so next we had, so since I'm closer to 156, I think I'll go to 156 number 1, and then we'll go back to 263. Okay, 156 number 1. Okay. All right, so here they give us the function f at x equals x to the 4th minus 1 over x to the 4th. And they want us to find f prime and f double prime. Okay. So in this case here, I could certainly subtract these two expressions and write them as a single fraction and work with the quotient rule. But I think it's much easier to keep these as individual terms, since they're both just powers of x, and this is much faster to take the derivative. Okay, so let's start with f prime. Okay, so here we have the derivative of x to the 4 is just 4x cubed. And then here we've got minus, and the derivative of x to the negative 4. Notice I open up a bracket because I'm going to have another negative here. So negative 4x to the negative 4 minus 1 is negative 5. Okay. All right, so at this point here, if I wanted to write this in, a nicer form, if I want to simplify it, I would probably write it as 4x cubed plus 4 over x to the 5. Again, I could add these together and write it as a single fraction, and that's perfectly fine. But when I'm taking the second derivative, I'm definitely going to stick with this version of the function, or of the derivative, okay? Because this is much easier to take the derivative of. So now let's go ahead and take that derivative. So here, 4 is just a constant, okay? And then times the derivative of x cubed, which is 3x squared, okay? Then plus, again, 4 is just a constant. And then here, the derivative of x to the negative 5 is negative 5x to the negative 6. And now I can go ahead and simplify if I like. So what do we have? We have 12x squared and then minus 20 over x to the 6th. And again, nothing stops me from writing this as a single fraction. Like if I had to determine where it was equal to 0 or anything like that, I could simplify further, but I think we can just leave it like that. All right. So any questions, again, especially from whoever asked them? All right. Okay, but something to keep in mind. Notice I'm going to try to always use the easiest scenario when I'm finding the derivative. So if you have a constant over power of x, or in fact, any power, I'm just going to rewrite it as a negative exponent and use my power rule. Same thing here. Okay, there's no questions. Let's move on to the last one I had, which was 263. 23A. All right, so 23A. Oh, it's another second derivative question. All right, so this is page 265, number 23A. And the function that we're given is 4 times sine squared of x minus 2. Okay. Now, normally I wouldn't necessarily do this, but it might not be a bad idea to use that little trick that I gave you of rewriting sine squared in terms of what it actually represents, which is the whole sine expression all to the power 2. This might make it a little more straightforward in terms of using the chain rule correctly. Okay, so let's start with f prime. So again, the 4, just a constant. It's just taking 4 times the derivative of that function there. So the 4 stays out there. So let me put some big brackets here. Now this is where I see I'm going to have to definitely use the chain rule once, because whatever's inside this square bracket is being squared. So the derivative of u squared is just 2u. So 2 times sine of x minus 2 to to the power 1. Of course, we're not going to write. Times, now we have to take the derivative of this inside function, but this inside function needs the chain rule because I know how to find the derivative of sine x. That's not what I have. I have the derivative sine of x minus 2. So here, that x minus 2 is going to be like my v. So what is the derivative of sine v? It's cos v. Okay. And now I'm going to multiply it by the derivative of v. Now, it just so happens that the derivative of x minus 2 is just equal to 1, because 2 is a constant and the derivative of x is just equal to 1. Okay. The reason why I write it out is I want to make sure I don't forget, because if that had been 2x minus 2, then the derivative would have been 2 and not 1. Okay. So notice how I write out that I had to take the derivatives of 3 functions. The outermost function was the u squared. The next outermost function was the sine v. And then finally, the derivative of x minus 2. Okay. Any questions on that first part? Okay. So before moving on, I'm going to clean it up before taking the next derivative. So here I've got 4 times 2 is 8. And then here I've got sine of x minus 2 cos of x minus 2. Okay. And this is where, well, I'm going to do it in 2 ways. I'm just going to do it the more straightforward way, where I'm not just thinking take the derivative, but then I think I see another option that would actually make my life a little easier here. But let's do option 1 here. So f double prime. So again, 8 is just a constant. And now let's take the derivative using the product rule. Now notice in each of the cases where I need to take the derivative, I'm going to have to take the chain rule. Okay. So the derivative of the first function, so the derivative of sine u is cos u. And then the derivative of u with respect to x, again, just happens to be equal to 1. Okay, times cos of x minus 2, because that's the second function. Then plus the first function, sine of x minus 2. Okay, times the derivative of the second function, which is going to be the derivative of cos u is negative sine u, times the derivative of u, just happens to be equal to 1. Okay, and now here we see that we can do some simplifying, because here this is just cos squared x minus 2 minus, because I'm adding the negative, minus sine squared of x minus 2. Oops, should be another round bracket there. And I could leave it here, or I could recognize that this is something we've seen before. We know that cos squared plus sine squared is equal to 1, but you might remember that cos squared minus sine squared is actually equal to, so let's recall here, let's do a little recall, that cos squared theta minus sine squared theta is equal to cos of 2 theta. Okay, so what I could do is I could rewrite this expression here as the cosine of 2 times whatever is in the bracket. Okay, and so this simplifies it quite a bit. Okay, now this is, playing around with our trig identities. But again, if I was just asking you to, find the second derivative and without simplifying, and you left this thing here, that would be perfectly fine. But eventually we're going to have to start working with these derivatives, and we can see how we use our algebraic skills, in this case here, our trig identities, to help us simplify these expressions. Now, I said this was one option Does anybody see, maybe based on what I just brought up here, does anybody see how I might have treated this a little differently? I'm curious if anybody saw something here. Sine times cos, does that remind you of anything? Well, folks, I have to say this year, it is the quietest tutorials I've ever given. Anybody think sine times cos, and you have this factor in front, does that remind you of anything? Well, it should, because 2 sine theta cos theta is equal to sine 2 theta. Okay, so if I go down here and I rewrite this expression as 4 times 2 times sine x minus 2 cos x minus 2, I can rewrite this expression in here as sine of 2 times whatever that value is. And this answer up here might start making a little more sense, because now, that was f prime, of course. If I take the derivative from this expression, let's see what we get for the second derivative. Okay, 4 is just a constant. This whole thing here is like my u. What's the derivative of sine u? Cos of u. Okay, times the derivative of u with respect to x. Well, it's just, remember, that's a constant. 2 times the derivative of x minus 2, which is just 1, times 2. And lo and behold, we get the exact same answer as we did here, with a lot less work. Okay, so again, we see how we can use the power of the trig identities to make our lives easier when working with trigonometric expressions, and now trigonometric derivatives. Okay, so again, as I said, this is not the type of thing I would expect you to be doing in this unit, but in future units, when we have to actually work with trigonometric derivatives and second derivatives to solve problems, then it might be useful to use the power of the trigonometric identities. Okay, so those are all the problems that I've received. Is there anything we want to ask about any of the particular problems, or any other questions, or any conceptual things we want to ask about? Okay, so somebody to do 112.23c. 112.23c. Yeah, let's go to that. No, what value? Each not differentiable. Okay, perfect. All right. So let me just write down the function. F of x equals the square root of x squared minus 7x plus 6. Okay. And they're asking us when this derivative is not defined. Okay. So one thing we could do is we could try to draw the graph of this function here. Okay. So that certainly would be helpful. But if I can get away with not having to actually draw the graph, I think that would be good. Now, by the way, are there any points that you think we could easily find before even using the derivative? Because that's going to be my strategy is to actually do it algebraically here instead of trying to draw the graph. But can you tell me what x values will definitely not be differentiable for this function? Well, take a look. I've got this square root. I've got an expression inside a square root. What values would be automatically eliminated from being differentiable? Yeah, anything that makes this expression negative. Okay, so I'll deal with that later on. Okay, but, and this is something we had seen very briefly when we were looking using the graphs, but we also saw that the derivative function is helpful in telling us where something is not differentiable. So let's actually find the derivative of this function. And of course, I'm going to think of this as x squared minus 7x plus 6 all to the 1/2. So that when I take the derivative, it's a lot easier to see. Yes, I'm taking the derivative of u to the 1/2. So 1/2 u, which is x squared minus 7x plus 6 to the negative 1/2 times the derivative of u with respect to x. And so that's going to be 2x minus 7. And when we clean this up, of course, this is what's going to help us determine where this is not going to be defined, because this negative 1/2 is going to take this expression and put it into the denominator. So the only thing left in the numerator is the 2x minus 7. This 2 obviously is in the denominator. And then here, this negative 1/2 is going to be a positive 1/2 when I bring it into the denominator. Okay. And so now I can tell by looking at the derivative when this thing is not going to exist. So first of all, as we said before, we knew that from just looking at the function itself. Anytime whatever's in the square root is negative, that has to be eliminated. But what else has to be eliminated now, given where this square root lives? We also have to eliminate anything that makes it 0. So now what we have to solve is we have to solve where x squared minus 7x plus 6. Okay, if we're looking for where it's not differentiable, we need to determine when this expression is less than or equal to 0. Okay, so here we could tell anytime it was less than 0, the function doesn't even exist, so it clearly can't be differentiable there. But now after having taken the derivative, we see even when it's equal to 0, this derivative won't be defined. Okay, and this is a fairly easy problem because it's factorable. So here we have x minus 6, x minus 1. And of course, how do we solve these inequalities? We just draw ourselves an easy graph, because we know this function behaves like this. Okay, since it's a quadratic opening up with these zeros, so everything between 1 and 6, including 1 and 6, are where this derivative don't exist. So here, not differentiable, sorry, on, and what's our interval? From 1 to 6, inclusive. And why? Since f prime at x does not exist at these values, if we wanted to justify. Okay, so like I said, in the past, when it was an easier function, we might have been able to, work with the graph. I might try to guess at what the graph looks like, but here, using the derivative function itself, I was able to determine when this derivative doesn't exist, and it's when the expression inside the square root is negative. That's just the natural order of things with square roots. And of course, anything that makes the denominator equal to 0, that also needed to be eliminated. All right, any questions on that? No, okay. Last call. Yeah, no problem. Any other questions we want to look at? Or like I said, even if it's a general conceptual thing, doesn't necessarily have to be an assignment question or homework question. Okay, looks like there's nothing else, so we're gonna stop the recording.